Okay, in this one I'm going to be talking about the chain rule. Okay, and you're very familiar with the chain rule. You went through a whole year of single variable calculus, and so I'm just going to remind you kind of how this went. Right? If we had y equals f of g of x, it's kind of a composite function situation. Then y prime was equal to f prime of, leave the inside the same, and then multiply by the derivative of the inside. Okay. But remember, we don't really have, or at least not yet, we don't have like f prime for when f is a function of x and y, right? We have partial derivatives. We'll have something called the total derivative, maybe later in this video, but not something that we're going to really use to talk about, the rate of change of the function, right? We kind of have some sort of disclaimer there. Okay, but then a better way of writing this, or a way that maybe made a little more sense in single variable, was if you had y equals f of u and u equals, g of x, then dy dx was equal to dy du multiplied by du dx. Okay. And this is going to look a whole lot more like what we're going to do today. All right, so before I really go that far, I need to talk about a kind of a concept that we don't talk that much about in AP calculus, but kind of the differential of c. And so what I'm going to say, I'm going to propose that the change in z is equal to, well, that would be z2 minus z1, or some f value minus some previous f value. So what I'm going to say is, well, it's going to be what happens when I bump up f by some amount. Okay, so f of x plus delta x and y plus delta y minus f of x and y. Kind of taking this as self-evident. This is the original z. This is what happened to z after I increased x and y by some amount. Okay. I'm going to say, well, if this function f is differentiable, we can approximate it at a point using the tangent plane, which is something I've talked about in a previous video. So I'm going to pause the video for a second and try to draw a surface with a tangent plane on it. There you go. I'm not entirely sure if these these ribs are helping, give it some depth, or if that's just making it look weird. But either way, I'm drawing you. We've got some sort of surface in space, z equals f of x and y, and there's a tangent plane at some place where it's smooth enough to lay it in. And what I'm going to remind you of is something from last time, is the equation of this tangent plane. And that is z minus z0 is equal to fx times x minus x0 plus fy times y minus y0. Where x0, y0, z0 is kind of the point of tangency. Okay. And I'm going to say that, near the point of tangency, we can approximate f with this. So when I go to actually, look at this, use the tangent plane to approximate this. And so how did I write this? If f is differentiable, the tangent plane approximates f. And so, so I'll say is that f is, approximately equal to z in that z sense, which is equal to z0 plus fx times x minus x0 plus. So the change in z being f of x plus delta x, I should probably just jump in and do some algebra here. Delta z is going to be f of x plus delta x. Well, that'll be z0 plus fx times, replace x with x plus delta x. And right here, this is not like fx of that is the the value of the partial derivative at the point we're interested in, multiplied by all three of these things. So I am going to distribute that. Okay. Plus fy, how this is going to go y plus delta y minus y0 minus this f of x and y. Okay. Once you distribute, and rather than writing out z0 plus fx times x minus x naught plus fy times y minus y naught, I'm just telling you that's what I'm thinking of this as, is basically all of this minus the delta y's. So I'm going to go and kind of clean it up mentally. Is for this z0, when I subtract off f of x and y, which is approximately equal to that, I'm going to subtract off the z0, and that'll be gone. Okay. Then what I'll be left with is, fx times x minus x naught. That's encapsulated over here. I'm going to subtract that away. All I have left is fx times delta x. And then I will have, in the same way, that fy times y minus y naught. Well, I'm going to have one of those over here, and it will subtract away as well. So I'll have fy delta y. Okay. Now, I'm going to take a second and come back to this before I get you kind of the formula for the derivative of z with respect to t. So right now, we are used to a two-variable function, and maybe I'll write this in pink. We're used to a function which is taking in a two-dimensional vector and giving us back a real number. But the question is, what if x and y both depended on some time parameter? Okay, we've seen curves in the plane that depend on time parameter. That was an AP calculus. So it's not totally out of the realm of possibility that x and y could both depend on some other parameter. So if we have, a composite situation, say, and I don't really even want to get into naming these. I'm going to try to draw you the schematic diagram. Is that we have t, and then that goes to x of t and y of t. But then these go together to contribute to some f of x and y. Really, f is, if you trace it all the way back, depending on t. Okay? So I could take the derivative of f with respect to t in the single variable derivative sense, limit of rise over run, because if you go and you plug these in, you'll see that f does in fact depend on t. And one that I'm going to talk about, and I don't know that I've kind of budgeted enough room in my shot for this, but I will, maybe I'll just mention it, is x equals cosine t, y equals sine t. We know what that traces out. That traces out the unit circle. And then some function f of x and y, I say that's x squared plus y squared. Okay. Well, you know what that's going to be. F is going to constantly be 1, so I should be able to take its derivative and show it goes to 0. And I think that's what I'll wrap up this video with. Okay, but I'll come back to that. So if I have, z, which is f and x and y, depending on some sort of t, I'm going to be interested in the change in f, or the change in z as t goes towards 0. And so I'm going to take delta t not equal to 0, right? Close to 0, but not equal to 0. And so I can divide everything by delta t. So I'll just go do that. And so this is kind of where we're going to see the actual, the chain rule as you would see it in the textbook. Okay. As delta t goes towards 0, z depending pretty much entirely on t, up to that interpretation, I'm going to call that dz dt equals fx, that's the partial of f with respect to x, partial f with respect to x, multiplied by delta x delta t. Okay, as delta t goes towards 0, the limit of delta x over delta t is going to be dx dt. Plus, okay, it's the partial of f with respect to y, so partial f with respect to y, times, as delta t goes to 0, delta y over delta t will head towards dy dt. Okay, and so this is the chain rule for a function of two variables. And I will need this to, prove various things about the gradient, to explain why that nice dot product formula for the directional derivative works, all of that. And so I think what I'm going to do at this point is I'm going to go and kind of call back to the example I was talking about, and hopefully it'll work out just like we expect. Now, actually computing derivatives using the chain rule, not going to be a very important part of this course, but some of the concepts that we're going to work with are going to rely on this idea. So that's why I needed to show you, where does this formula come from? Why is there a sum here? Because basically the change in z is coming from contributions made by changes in x and changes in y. All right, so for example, like I was saying, I've got f of x and y is x squared plus y squared, where x is cosine t and y is sine of t, right? So the domain of f is actually going to be, just the unit circle. And the range of f, well, f is only going to map to 1 because we know cosine squared t plus sine squared t equals 1 for any t. Okay, so really this is going to have, f is constantly equal to 1. So when I take the derivative of f with respect to t, I should get 0, right? So what I've got is, maybe I'll just kind of take some partials and take some derivatives, just so I can put this all together. I'm going to say is equal to 1. And maybe I could say is constantly equal to 1. And so df dx. That's equal to 2x. df dy is equal to 2y. Okay, dx dt is equal to negative sine t. And dy dt is going to be cosine t. Okay, so the derivative of f with respect to t is going to be df dx times dx dt. So that's 2. Is 2x times negative sine t plus 2y cosine t. You might be like, wait a second, dude, this was supposed to be a function that depended on t, and this was supposed to come back 0, like what's happening here? And I'll admit that while I was writing this out, I had not actually worked this example all the way through. I was not sure what was going to happen, but x and y, we have formulas for these, right? So we have x is cosine t. This is negative 2 cosine t sine t plus 2y is going to be 2 sine t. And, okay, this is not exactly the same, but I know that 4 times 5 is the same as 5 times 4, so I'm going to say cosine t times sine t is the same as sine t times cosine t, and these are going to add to 0. Kind of like we had expected. Okay, this is how the multivariable chain rule is working, and we will use it to get to some results here in the next couple of videos.